Greetings! In this episode we have a new denizen for the Tektronix power frame, the Series 5000 power frame. We've done 2 episodes before where we got 2 modules, cleaned them up and saw them work. So here's the third one. This one's special. This one's double wide, uses 2 slots, and it's the FG-5010 programmable 20 megahertz function generator. One thing unique about these modules is that front panel real estate is at a premium. So they got to cram a lot of stuff onto the front panel and still make it usable. The funny thing about this one is that it's not just the front panel that dictated the width, but there's a lot inside it, and we'll have a look at that later. But yes, it's a function generator. What can I say about that? It's a function generator, and it's by today's standards it's a little basic, but it still does the job with a very small footprint. So let's go over what everything on the front panel does. The top strip is the display. It's got room for a 4-digit coefficient, 2-digit exponent. It's base 10, of course, and enunciators over here that tell you what mode you're in and what you're supposed to be doing, and if there's an error. Then we get to these buttons. Let's do these in a column fashion. So there's a function. You select the function. You can get either a square wave, a triangle, a sine, or you can hold whatever it is you've selected. The second column here is the mode you're in, which is either continuous, triggered, gated, burst, and the burst you can basically specify how many cycles you want to see in a burst, and a phase lock. Underneath that is the capability to amplitude modulate the signal with an on-off switch and a BNC input. So if you want to do that, you need at least one other module to generate the AM signal for you. Next, we have the trigger, the external trigger or gate come in. I mean, a trigger is just a blip, a quick strobe, whereas a gate, as long as the gate's high or active, it will output the function, and the minute the gate goes inactive, the output will go back to 0. This will show you whether you're getting triggered. You can manually trigger what you have, and you can also change the slope of the trigger over here. Then we get to this group of parameters here, which let you select what it is you want to enter. Frequency, amplitude, offset. The offset just adds adds a constant to the amplitude. Basically, it shifts the signal up or down. Number of burst. So if you select the burst function, here you specify how many cycles you want to be contained in a burst, the phase of the signal, the symmetry. The easiest, I mean, it'll skew the signal. It'll be most obvious in square wave, where you're basically setting the pulse width, but it'll also cue a triangle and a sine. Then we have increment and decrement buttons, because as you'll see later, we have to enter everything. There's no turning knobs here. you have to actually enter. If you want a new frequency, you got to enter it. But if you just want to increase or decrease the current value that you have, you can use the increment and decrement buttons over here, and you can set the increment and decrement size by pressing this button, and then basically you can also select the least significant digit or the most significant digit and just enter what you want to see. Let's see, we can also frequency modulate the signal through this input and also apply a voltage controlled filter over here. We can store and recall setups. This will output a trigger. Regardless of the waveform, it'll just output a periodic trigger based on the frequency you've selected. And then of course we have the actual signal output over here, which has an on-off switch and you can complement the signal over here. And that sums up what the front panel allows you to do. Well, let's see how she performs. So we're going to use the Tektronix digital scope because it nicely tells us the frequency, so we can do a comparison to see if the frequency is actually what we asked it to be, and it'll show us the maximum voltage to so see if our amplitudes are correct. The amplitude is supposed to go up to 20 volts. So yeah, let's see. Okay. So it comes up in sine mode, continuous, the output's off, and the frequency is set to 1 × 10⁻³ . So we are set at 1 kHz right now. And let's see, the amplitude, that's set at like, what, 1, 2, 3, what is that, 0.5 volts. So let's change the amplitude to a more reasonable 2 volts. We're in amplitude mode, so we hit 2, enter. Offset should be at 0. We want it centered on this center line. Number of bursts doesn't matter, it defaults to 10. Phase 0. Symmetry is 50%. So that would give us a 50% duty cycle on the square wave, or should. Increment size, it's set to 0, so it won't do anything, but, well, okay, so let's start with the square wave and turn the output on. Boom. So okay, we're set to 1 volt per division. Our amplitude was 2 volts, so that's right on. And if we look at the frequency over here, it's 1.000, oh come on, 1.000. It's dancing around a little bit, but it's pretty darn close to a kilohertz. So now let's look, well, actually let's bump the amplitude a little bit. It's 2, so let's make it 4. And you can hear the relays click because they route a lot of signals. Instead of having like a single DTA converter, they actually switch on a different quadrant of the part that generates the output. Also in the beginning, you may have noticed, you heard a whole bunch of relays click. So yeah, they use a relay for routing signals a lot in this. But at this low frequency, it's showing a perfect square wave. Well, at least visually. So then we go to the triangle, and it shows you a razor sharp triangle. Don't touch the tip of that, you'll draw blood with it. And of course our third option is the sine wave. So all of that seems to work really well, but yeah, we're at a low frequency. So let's jump up a little bit. We are at 1 kilohertz, and well, let's go to 100. So we go to frequency. We want 100 times 10 to the power of 3. Boom. So now our signal is 100K. And there's our sine wave. And yeah, it's on 100K. Shape is still very good. Still we have a razor sharp triangle wave. And a good looking square wave. So let's try out the symmetry right now, which is set to 50%. So if we set it to, say, 75%, we should get a 75% duty cycle. 75%. Boom. That works nicely, and then conversely we go to a 25% duty cycle. And there you have it. So that'll also let us, let's see, does it complement it? Yep. So the complement button works too. So far, so good. So we are at 100K. Well, first of all, let's set the symmetry to 50%. Where are we here? 50. Sorry. Oh, and then let's see what the symmetry does to the other waveforms. Here's a triangle. I'm not exactly sure what that's going to do, but hey, let's try it and see what happens. So 75% it's going to. Alright, so it leans it to the right. So if we do 100%, we should get a sawtooth. Well, there's still a slope on this. Oh, I see. It went to 10. It didn't like the 100. Okay. So let's try 99. Doesn't like 99. So I'm not exactly sure here, but what the upper limit is. Well, let's try 90. Okay, clear. 90. There you go. So I bet you it's the range is between 10 and 90%. So that can easily be checked. Yep. Okay. So it doesn't let you go to the extremes. But let's go back to 50. Okay, now down to the sine, same thing. If we change the symmetry to 90%, it should lean it to the right. If we go to 10%, should lean it to the left. And there you go. So that part seems to be working nicely. Now it does claim to be working up to 20 megahertz. We're looking at 100 kilohertz right now. So let's see what happens to the waveform as we start bumping the frequency. So let's go to 500 kilohertz. 500 times 10 to the power of 3. (500 kilohertz). Sine wave looks good. Triangle still looks really good. And the square is also following. Alright. So then we go to, say, 2 megahertz. Let's see what that'll do to the square wave. So that's 2 exponent 6. Yeah, we're beginning to see some distortion here and here, but that may have something to do with the cable. You probably have a bit of an impedance mismatch here, and I have no way to adjust it with this cable, so, but that's still pretty good, running at 2 megahertz. The other waveforms, triangle's still good, even though it's getting a little fuzzy here and here, even though the connecting lines are still pretty straight. And the sine, also top and bottom are getting fuzzy, but it's still holding its own. So next we'll go to 10 megahertz. Still, we have a pretty good looking sine wave. Triangle's good. Square wave is starting to get distorted. That's because the spectrum of a square wave has many harmonics in it, and at 10 megahertz, I guess it's hard to tell whether it's the scope, the signal, or the cable, but the scope's rated at 200 megahertz, so still good enough. And then of course we go and hit the maximum, but let's switch back to the sine first, and the sine still looks, yep, we're at 20 megahertz. Sine looks pretty good, and as a matter of fact, the fuzziness at the edges is a little less than it was before. The triangle is definitely beginning to round corners here. And the square wave is getting real squishy. But it delivers at 20 megahertz. So then let's see if the output can actually reach 20 volts. In order to do that, let's go down on the frequency so we get a cleaner display. Let's do a megahertz. And our amplitude right now is 4 volts. So let's turn the right knob and set it to, well, let's set it to 5 volts per division. So at 10 volts we should be occupying 2 divisions. And at 20 volts we should be occupying 4 divisions. And there you go. As specified, it outputs at 20 volt amplitude. Now the offset, for instance, will let us move the wave up or down, but let's see first. Is the triangle good? And the sine's good. And so as an offset, it has none now, but since we have 5 volts per division, if we give it a 5 volt offset, it should jump up 1 division. So and that works too. And we should also be able to give it a negative offset. So let's do 5, change the sign, and that also works. Well, it's doing well. And yes, what we haven't looked at is using external outputs. External inputs, I mean. But I think this is enough to prove that this thing basically works. And it's pretty clean. Kind of, yeah, you know, the a square wave is always worst case because of the number of harmonics in it. And a sine wave is best case because of the number or lack of a number of harmonics in it. And the triangle looks pretty good all the way around. So maybe now that this all seems to work, let's have a look. Remember I referred to the width being dictated not just by the front panel but also what's inside? Let's have a look, see what's inside. Here's the right side of the instrument as seen from the front. And yeah, this is one of the analog output boards. Yeah, I mean, it looks like a joy to work on, but it's pretty cleanly laid out. It almost looks like HP quality, but just almost. Gold-plated connectors, gold-plated interconnects in here. Now, the left side, that's the digital board. And again, what I failed to mention in the beginning is the displays in front, they actually show you the number that you've entered. It's not actually measuring frequency or amplitude or anything like that. It just tells you, hey, this is the number you entered, and this is what I'm going to try to output. And it's got the this is the GPIB controller chip, a Motorola 6802 8-bit processor, a ROM, a 6522 parallel interface adapter, and a bunch more digital stuff. Now I'm looking in here, I cannot see a battery. Remember, it said that it would save setups, but I don't see a battery here, so where could that be? Oh, and then there's a dip switch over here to select the GPIB ID. But that's not all. Here's the top of the module. And feast your eyes on this. There are 1, 2, 3, 4, 5, 6 PCBs in here. Basically, this is like a backplane over here that they all plug into, and the front panel also plugs into. And yeah, it's repairing this. I mean, okay, you know, if the microprocessor doesn't run or something, fine, you can test it. If the output board has a problem, yeah, it's in plain view and you can test it. But all the other boards, good luck. So from what I gather is there's one board, actually two boards that generate all of the voltages this requires. This, of course, is a CPU board. This is like another interface board. And then these are basically the function boards, the actual function, the ones that generate the waveforms over here. Everything is shielded. Well, everything that needs to be shielded is shielded. You can see another big shield inside here. So yeah, I'm impressed. I'm actually impressed. The circuitry, fine, they have engineers who will design this. It's still admirable, but not something, I guess, as they put it, it's their job. But the person who put it all together, who managed to cram all of this stuff into a double wide module, I think that's the part that is really, really, really admirable. But there you have it. That's what it looks like inside. There's the underneath. Just get the same view. But if you want to get to these, I mean, you have to remove everything I've removed. You have to remove the back cover here, and then start pulling boards out from their slots in the back plane. And live testing on these would be pretty difficult. Finally, we have the rear. It uses two slots of the power frame and the GPIB interface. And that sums up this beautiful module. As I was reassembling the module, I noticed an inventory tag I hadn't seen before, which tells us where this was coming from. Come on, don't tease. Look at that. Well, here's a family photo for the album. 3 working modules in it. Thanks for coming along on the journey and seeing these checked out and cleaned up. But yeah, there's a fist-sized hole here that'll need to be filled. And as soon as it gets filled, you'll know, if of course you've subscribed and hit the notification bell. Thanks for watching. We'll see you soon.